Professor Eric Rignot, Professor of Earth System Science at the University of California, Irvine, and also a consultant at the NASA Jet Propulsion Laboratory. I was born in France, and I spend actually a little bit more of my life in the US now, so I'm not sure where I am from anymore. A lot of the work we're doing is funded by NASA. We're using satellite and airborne resources from NASA and other space agencies, and we use those to study glaciers, ice sheets. The observation of glaciers started to become a little bit more intense and focused in the 1990s. We developed airborne programs at NASA in support of satellite programs. The goal back then was to figure out what are the ice sheets doing in response to climate change. Are they growing? Are they shrinking? What does that mean for the future? The importance, of course, of glaciers and ice sheets is that they're going to raise sea level. That's the main implication. There's other potential ramification of the melting of land ice into the ocean. It might affect ocean circulation and marine life and other aspects, but the main one is the impact on sea level rise. So when you have a system that accumulates more mass and being dispersed, it's going to grow. Sea level is going to be lower. And the opposite situation is when you have too much mass flowing out of the ice sheets compared to what is accumulated in the middle as snowfall, then you're going to contribute to sea level rise. You're moving a piece of land ice resting on land and melting it into the ocean that results in a higher level of sea. So in the line of work I've been pursuing in the past 25 years, we've used satellite data to map out all the glaciers, how fast they flow. We combine that with airborne measurements of ice thickness, so we can measure the flux of ice all around the periphery of Greenland and the Antarctic and look at the changes with time. And we've coupled these results with reconstruction of what we call surface mass balance, essentially accumulation of mass as snowfall in the center of the ice sheets. So we could compare the two numbers, how much is coming out versus how much is coming in. So we do that. We can reconstruct on a monthly basis what the ice sheets have been doing. And we also compare that with other techniques. There's other ways to look at ice sheet mass balance. One is to measure the height of the snow and ice surface and how it changes with time. So you effectively monitor the volume changes of the ice. And it's important for us to compare their results with what we have. And then there's a third technique since 2002, which is the time variable gravity mission from GRACE, which directly measures the changes in mass below the track of the satellite. It does not operate at the same level of detail that we have with the other techniques, but that technique directly measures the change in mass. In some of the work I do, we compare two big numbers, how much ice is flowing out versus how much snow is falling on the ice sheets. These are two big numbers, and we're interested in the difference. And we want to know if there's a difference between the two of the order of 5%. If we have an error on that of 30, 40%, we're not good enough. We need to beat down the noise level much lower than that. One area we've particularly focused on is the Amundsen Sea sector of West Antarctica, right? Because we had indications in the 1990s that there were some big changes going on. So this looked exactly what people had projected back in the 60s and 70s, that this part of West Antarctica was slowly draining out to sea and there was no way to stop it. In Greenland, we have something similar. All the glaciers are losing mass in Greenland, some faster than others, but all of them and all around Greenland. And the northern part of Greenland, the floating sections are falling apart already. We are more concerned especially about what we call the marine-based parts of the ice sheets. So these are places where the bed beneath the ice is laying at elevation below sea level, which means when the ice is removed from these areas, the ocean water will replace it and keep following the ice and melting the ice away. We have three big basins like that in Greenland with what I call floodgates at the exit point of the ice. And we've looked in detail to what's happening at these floodgates. And 2 out of the 3 main floodgates in Greenland have been opened up already. and can potentially contribute 2-meter sea level rise down the line. The level of mass loss from the ice sheets is way ahead of what models have predicted. It's happening way sooner and faster than what we anticipated. There are also other important aspects, such as it's important to look at these ice sheets more than just a few years. It's critical to look at all of them, the entire ice sheets in detail, and have several decades of observations. That's why I think we're coming a little bit more strongly about conclusions about what we're seeing in the polar regions, is because we have a pretty solid now Earth observation record. And also we're able to articulate more clearly that we don't need this record to stop now. It's critical to continue these detailed observations of what's happening in the polar regions if we want to understand very well what's happening and also make projections that are a bit more reliable down the line. We have two major clues about what may be laying out ahead, and I call that sea level commitments. The sea level commitment we're making in West Antarctica is a 1 to 3 meter sea level rise, 1 meter from the Thwaites Pine Island Basin alone. But models all agree that if that basin goes down, the rest of West Antarctica will follow, and that's a 3 meter global sea level rise. In Greenland, as I mentioned, these 3 floodgates that opened up, 2 opened up widely. That's a 1.6 meter sea level rise on top of the 3 meters from West Antarctica, and there's a potential for the other one to also go. I think it's going to go. So we have a potential 6 meter sea level rise down the line. We have clues also from the paleoclimate record, where people look in detail at what happened in the Eemian 125,000 years ago, when the temperature of the Earth was half a degree more than present, or maybe we're just right there. And they figured out sea level was 6 to 9 meters higher than today. 6 to 9 meters is a lot. There's probably not enough ice in Greenland to justify that. Not enough ice in Greenland and West Antarctica to explain the 6 to 9 meters. So we think these numbers indicate that something in East Antarctica also is going to have to change. So we have these numbers which seems to converge a little bit towards definitely multi-meter sea level rise down the line with a climate which is about 1.5 to 2 degrees above pre-industrial conditions. Societal impact, impact on coastal population, immigration, infrastructures start to be serious at 1 meter. 1 meter is a big deal for a lot of the world population. 6 to 9 meters is not good news. It's not something I don't think the planet wants to commit to. But if we stay in a climate system with global temperature 1.5 to 2 degrees above pre-industrial, we have to grow to the idea that this is what we're committing the system to do, 6 to 9 meters sea level. I think that's the most important message that came out of all these studies in the past decade. There's different aspect to this, right? One is, are we going to really hold the climate system to 1.5 and 2 degrees? You could argue, on one hand, this is a bit wishful thinking. On the other, there are the Paris Accord, and it's the first time that all these countries in the world decided we're going to do something about this. So we'll have to see if they actually pursue that actively enough to make it happen. As of right now, it doesn't look so good, but we have to be a little bit more optimistic than that. And then the second aspect is, how fast are we going to get to this 6 to 9 meters sea level rise? It's going to happen over what I would call a human life cycle. It's not going to be something that you care about for your grandchildren. It's something you might start to experience during your lifetime, and your kids will definitely feel all of it, and your grandkids will look at you and say, what was grandfather doing about this? If we control our carbon emissions today, you have to appreciate the fact that it's going to take 30 to 40 years to really see that showing up in the climate system. I'm going to try to stay as healthy as I can, but I don't know in what state I'm going to be in 40 years. 2050 is going to be kind of a turning point. For the ice sheets, if you look at the model projection, most of the sea level rise will come kind of after 2050. It's something that ramps up. We're only at the beginning here. It's already, what we're seeing is already pretty significant, but it's going to ramp up and go bigger. And really after the 50s, it's going to take off. I may see that, I may not. What I hope we won't see is some kind of non-linearity in the system, thresholds that are being reached, and the ice sheets or the ocean doing something awry, and it's changing state into something we kind of feared, but we're not sure if it could happen or not. Right? All of that, what I've been talking about so far is as if things that we're going to proceed smoothly down the line, but we really don't know. So we have to take everything with a grain of salt, and that's why maintaining a very good and solid observation network of the planet is critical. It's a little bit like a warning system. You want to see some of these things unfold enough in advance to prepare yourself. Right? We don't want to be in a situation like we were a little bit in the past, like an ice shelf disappeared in Antarctic. What happened? We missed it.